looking at question 1, we've got a proposed reaction mechanism for this reaction. It's not unusual to see stuff like this where there's not an actual substance, but they're giving you letters for the substances, right? So which of these do you think is correct? 1 finger for A, 2 for B, 3 for C, 4 for D. Put up your hands. Okay. Seeing lots of 2s, that is correct. How do we know that Q is an intermediate? Leaf? Yep. Yep. So if we were to put this together to make a overall reaction statement, that would be our we would cancel out the Q's, right? What's N? Ella? It's a catalyst because it starts off in the reaction, but then it's regenerated in the over the course of the reaction. So that would, and also would not appear in your rate equation for this. So yes, B is the correct answer. How about question 2? Again, give me A, B, C, or D, 1, 2, 3, or 4 fingers up. All right, good, looking good, yep. How do we know that it's B? Ella? Okay, yep. Exactly. So the largest activation energy has to be the first step, and there have to be 3 transition states for our 3 different steps. Good. Great. So I just wanted to, since a lot of people were not here on Friday, go over this idea that we talked about sort of towards the end of class last time. Let me actually go back a little bit. We talked about figuring out the rate equation from the reaction mechanism. Talked about how if we have a multi-step non-elementary reaction mechanism, that the rate equation is going to be determined by the slow step. So if you look on page 11 and you look at the 2-step mechanism proposed for this reaction, we can see that the first step is the slow step, and so the only thing we're really looking at that's determining the rate is the reactants of the first step. There's only one reactant of the first step, so that is going to be the only thing that plays a role in our equation. So even though if this was an elementary reaction, we would say that this would be the concentration of NO2Cl squared. Because we only have one of them in our slow step, it's just going to be the NO2Cl concentration figuring into our rate equation. Okay. And then we looked at example 2, and we said, okay, well, now the slow step is the second one, but because one of the reactants of the slow step is our intermediate that's generated in step 1, we still do have to take into account the reactants in step 1, okay? And so we actually have to take all of the reactants into account. So we are going to have to add across, or add down on the reactant side to show that we have 2 NOs and 1 O2 that are playing into the rate of the reaction. So when the slow step is first, you pretty much are just looking at the reactants of the slow step. But when the slow step is second or third, you have to think about what is generating the parts that go into the slow step that's determining the reaction rate. Okay. So if we look at exercise 1 on the next page, page 12, we can look at this overall reaction, and we can look at the two steps. And how would you take a minute to think about how you would write the rate equation for this reaction if this proposed mechanism was correct? So think about what is the rate limiting step, and how would you write the rate expression for this? Good. Mm-hmm. Mm-hmm. Yes. Okay, so this would be NO2 squared. Remember, the 2 is the order with respect to NO2. So that's, if we have 2 of them, that's going to be the exponent in the rate equation, right? So if the reaction is second order with respect to the NO2, what is the order of reaction with respect to the carbon monoxide? What would you expect to happen if you did this reaction a couple of times and changed the concentration of carbon monoxide? What would happen to the rate? Yeah. It would stay the same. It would be 0 order. Okay, because it doesn't figure into our rate equation. So if this mechanism is correct, then and we don't see carbon monoxide in our rate equation, then we could do an experiment to test this and say, okay, if we change the concentration of CO, will we see a change in the rate? So that is what we can do when we have proposed mechanisms. That's something that we can do to not prove that this is correct, but at least prove that it is possible or prove that it is incorrect, okay? So that's what we're gonna get into next, all right? Is how we can take our theoretical information and understanding of how rate equations work with respect to our reaction mechanisms and pull in experimental data, okay? So I'm not going to go over number 2. The answer key is already posted. So if you want to practice that, you can do that on your own. Page 13, we can, if we're given either experimental data or rate equation that's been derived from experimental data, we can then use that to evaluate a reaction mechanism. So kind of backwards from what we were just talking about with the carbon monoxide, okay? So if we're looking at a proposed reaction mechanism, 2 things have to be the case. in order to say this is a possible mechanism. It has to add up to the overall equation. So when we cancel out things that are on both sides, it has to add up to the equation for the reaction that we know is happening, okay? And then the second thing is it has to be consistent with the experimental data in terms of the order of reaction with respect to the different reactants, okay? So we have this reaction here. We've got NO2, and we've got fluorine, and as our reactants, and we do a bunch of experiments, and we say, okay, based on our experimental data, we think that this reaction is first order with respect to each one of those reactants, okay? Which, again, you wouldn't think was necessarily the case if this was an elementary reaction. You would think it would be second order with respect to NO2 because of the coefficient here, but that's one way you can infer that this is not an elementary one-step reaction, okay? So this is based on experimental data, right? And you may be, for a question like this, you might be given experimental data, asked to determine the rate orders first, and then asked to evaluate a particular mechanism, okay? But we're given the experimental outcome, and now here is our proposed reaction mechanism. So what we need to do is figure out, does it sum up to the overall reaction equation, and is it consistent with the first order for both reactants? Okay. So first of all, we can look at, okay, how does this sum up? We can see that we have an intermediate, right? Our F singlet is our intermediate. So if we cross that off on both sides, then we end up with, and then we add on each side, we end up with the 2NO2 plus F2 yielding 2NO2F, right? So that is, in fact, what we get. You don't have to necessarily write it out if you can see it clearly that that's the case, okay? Is this consistent with this rate equation? Well, according to this reaction mechanism, this is our slow step, and these are our reactants for the slow step, and it's first. So we don't even have to look at the second step, because this is our rate determining step, and it starts us off. And so you can see that this is, in fact, first order with respect to both of those. So yes, this is a possible mechanism for this reaction. Okay? So all you're doing is making sure that points 1.1 and point 2 are fulfilled by the proposed mechanism. So this basically goes through exactly what I just did. So again, we're not saying this is the mechanism. We can't prove that this is the mechanism, but we can say it is possible that this is the mechanism. All right, so if we look at exercise 1 on the next page. Here's our reaction. Here's our proposed mechanism. Note that in this case, our rate limiting step is step 2. So we're going to have to make sure that we take into account how we get the reactants for step 2 in terms of our overall rate equation. Okay. So first of all, we add up our steps, canceling out anything that's present on both sides. Do the steps together add up to the overall reaction? Yes, they do. We can see that the NO-Br2 is our intermediate. That's present on both sides. We can see that on the reactant side, we've got 2 NOs and we've got 1 Br2, so that's all good. And yes. Is the rate equation consistent with the rate equation from, is the rate equation based on this mechanism consistent with the rate equation that we're given from experimental data? Yes, Jacob is correct. It is. Okay, so because this is our slow step, but we have to take into account how did we get the intermediate that goes into the slow step. So we really need all of this to be a part of the rate equation. Okay. So because these two are both yes, then possible reaction mechanism is yes. Okay. Does that make sense? Okay. All right, do question 2. My suggestion is to write out the rate equation based on the experimental data. They give you the information, but they don't write it out for you. I suggest that you write it out. I suggest that you check whether the steps add up to the overall equation, and then go from there. All right. So, how would you write the reaction expression for this equation? Who would like to give me a rate expression? what's in our reaction equation? Leaf? Oops, sorry, NO. Right, squared, yes. That's correct, okay? So the slow is our rate limiting step, but it comes second. So even though this NO3 is our intermediate, we have to take into account how we get the NO3. So again, we're going to need all of those to factor into our rate expression. So is this a possible reaction mechanism then? Yes. Okay. So second order with respect to NO, first order with respect to O2, that tracks. Okay? Question? Yeah.
So, in one of the other examples in this packet,
Uh-huh.
they had O2 that, I'm pretty sure they had O2 in the steps, but then they didn't.
Which page are you looking at?
Or maybe I'm not. Let me think.
Okay. If you can find it, I can pull it up. Oh, yeah, right. So when we were looking at this one, the CO is present as a reactant, but it doesn't show up in the rate equation because it's only in the fast step. So it doesn't matter how big of a concentration of CO we have, because the thing that's determining the rate is just the NO2 concentration. So we can have as much or as little CO, as long as there's enough, something to react with the NO2, then it's going to be not determining the rate. Second order. So we've got, let's see. So order of reaction depends on, with respect to any particular reactant, we can figure it out experimentally by saying, okay, if we double the reactant, what is the change in the rate? If we double the concentration of the reactant, what's the change in the rate? Because generally speaking, increasing concentration is going to increase the rate of the reaction, right? You guys have seen that in the lab and just general collision theory. But if we have something like the CO in that equation, changing the concentration of the carbon monoxide isn't going to change the rate of the reaction. And so what we would end up with is, as we change the concentration, the rate, that's first order, zero order, the rate would not change at all. Okay, so we would just end up with a straight direct or indirect, whether we're looking at the reactants or the products, straight line concentration versus time graph, and a flat line concentration versus rate graph, or rate versus concentration graph. If it was a first order reaction and we doubled the concentration, we would also double the rate. So that would give us a curved line for the data that we're actually collecting, right, for concentration versus time when we're collecting data across the course of the experiment. And then if we were to plot concentration versus rate, basically plotting the slope, the derivative here, we would end up with a direct relationship, one-to-one relationship. As we double one, we double the other. If we triple one, we triple the other. Okay. A second order reaction is where if we double the concentration, we end up quadrupling the rate. And that is because we have a rate expression that, where can we go back to? Where's our rate expression where the coefficient here is something other than 1. Okay, so if our coefficient here is 0, meaning that it's not even going to show up in the rate expression, then it's a 0 order with respect to that reactant. If this is a 1, or an invisible 1, that means it's first order. If it's a 2, that means it's a second order. You would go from there, but you're not going to be asked to evaluate anything higher than a second order with respect to a particular reactant. Does that help?
So that's why this is the reactions found to be second order when we set the equation.
Yes. So, yeah, exactly. Yep. Okay. So here, in this, on page 13, the example at the top gives us the overall reaction has 2 NO2s, but the first step is the slow step. When the first step is the rate limiting step, we don't care about the second step or any steps after that, because that's the thing that's going to determine the rate. That's the thing that's going to change things. And so it ends up being just first order with respect to NO2, but also first order with respect to the F2. Okay. So anytime you don't see an exponent there, it's a 1. Okay, so this is also consistent. All right, I would like you to look at the back of your warm-up and answer those questions. So you're being asked to evaluate some experimental data and determine what the order of reaction is relative to those 2 reactants, and then determine if the proposed reaction mechanism is possible. Okay? Open notes, not open friends or open internet.